I wanted to start off by asking, so who was here? I wasn't at Cassandra Summit last year, but I think I was at most of the ones before that. So I wanted to just summarize a few of the things that, if you were around then, you might remember some of these things. So back in 2011, we did some testing while I was at Netflix and on scalability, and we were running 24 nodes, and we weren't sure what would happen when we went to 48. So we tried scaling up, and it kept scaling all the way to 288. So I posted this blog post, which DataStax then turned into an advert, which I kept popping up on websites for the web for the following year or something. It's all, it scales. So that was good. And then we managed to persuade AWS to do solid-state disks. And then we hoovered up the entire supply of solid-state disk-based instances for about 1 year after that. So everyone else said, well, they exist, but you can't get them. So I'm sorry about that. But I did do some nice benchmarking. And the bottom right, it was very good to see Azure this morning launching 90 Cassandra nodes on stage, right? Because that was 3 years ago, I think, I did that with AWS. So, you know, good to see them catching up. But I did a side-by-side benchmark of solid-state disk versus regular disks. And that was actually one of the most fun presentations I did because we had no idea whether it was going to work. And we were doing stuff live on stage and deploying hardware and running a side-by-side benchmark. So that was a lot of fun. Anyway, so I used to be at Netflix, but I moved on. So now I'm at Battery Ventures. It's a VC firm. And these are all the different things I do now. I do obviously due diligence on deals for the VC firm, the companies that come in. I advise portfolio companies, give them technical support, sort of consultant to the CTO, scalability, cloud migrations, Cassandra migrations, and I'm responsible now for 4 or 5 companies, I think, switching to Cassandra, and they seem pretty happy about it. Networking with interesting people, that's all of you. If you want to contact me after this, I've got a few cards, but I'm easy to find. So just go onto Twitter if you want to talk about something, if you want to start a company, or you want to talk about using some of our portfolio company, interacting with people. I also mess around with some technologies, and I'll talk a bit later about some code I've been writing, which is this simulation thing. I also do a lot of conferences. I'm on the program committee, I present a lot, and I sort of travel around doing internal things, but I also do quite a few internal talks at companies. So if you're particularly interested in having me come and do an internal talk to kind of persuade your team that you should be doing microservices better or something, happy to discuss that and see if I can fit something in. All right, so topics for today. I'm actually going to start by talking about microservices from the point of view of why is this an interesting thing. It was good to see Sam Newman's Microservices book up in this morning when Jonathan put up the slide. So, you know, it's a hot topic. What's going on there, and why is that a Cassandra sort of tends to drive a lot of the back end for microservices ends up on Cassandra. I think it's a very good fit. And then I'll talk a bit more about simulating architectures. So, it really comes down to, you know, to sort of, you know, the canonical CIO, well, I guess canonical is a company, but the CIO that, you know, the generic CIOs that are trying to get stuff done. The kinds of things that they're struggling with right now, they sometimes call it the digital transformation or the sort of data deluge or whatever. But what they're really trying to do is align the IT departments with the business. And what does that mean? How do they get more product focused instead of more project focused? That's one of the big transitions. They're trying to help develop products faster because as software eats the world, everybody turns into a software company, and lots of people are getting into sort of existential you know, threat problems where if we don't innovate as fast as, you know, some, you know, Bay Area company that's got a big web services thing and you're an old enterprise, if you can't go that speed, then you're going to get eaten by them. And then also try not to get breached. There's a lot of focus on security and building systems that are much more robust now. So when we were trying to figure out architectures in 2009, 2010 at Netflix, we were listening to Werner, who was one of the original, this is part of the original idea behind one of the ways of doing DevOps, which is that if you built something, you run it. So that means the developers own things in production. Everything is self-service, so you're on call. And what that drives is that developers have to own building things and own deploying things. And it's really nice if you can deploy an entire global Cassandra cluster in a few minutes, right? Rather than having to go and argue with vendors for a few months or ops people, ops teams or whatever it is. If you just push a button and it happens, that is an incredibly powerful thing. This is much more than just, say, standing up a web page on Heroku, which you can do in a few seconds. The ability to deploy, terabytes or petabytes of storage trivially is really important. So it means that developers are responsible for going faster, and they're also responsible for the efficiency of what they're doing, how scaling it down when it's not being used and tidying up after themselves, and how efficiently they build product as well. And then they're also responsible now for the safety of it, how rugged or how secure systems are. And I'm not going to go through it. I don't have time to go through this much today, but if you look up my presentations online, I've got lots of presentations that go into this in a lot more detail. But this is what continuous delivery looks like nowadays. You're trying to observe what to do, orient yourself, decide which option to take, and then act on it. And for observe, it's really about innovation. Can you figure out what you should be doing? Can you find that customer pain point? Then you use big data, analytics to figure out what's going on. The typical thing here is you're trying to answer a question that's never been asked before. This is why you're grepping through log files, you're importing and cleaning stuff up. You're looking in places that no one's looked at before to find this piece of customer pain that's one entry sort of hiding in a lot of log files. Then you're going to figure out what to do. If you have the right culture, you can get stuff done quickly because it's all self-service, and you don't have to go and ask for permission, and you're working on small pieces of work, so it's easy. And then you use cloud to deploy this automatically. And that getting around this loop as faster than your competition is what makes you competitive nowadays. And a lot of people are suffering from this. So you don't just go around the loop, you bounce around it. So once you've got that, then this works fine as long as there's a handful of people. But what happens when there's a large team of people? What happens is if you build a monolithic application, you have 100 people all working on it, they keep stomping on each other's toes. They keep checking in code that breaks somebody else's code, and it's hard to get a build put together. And what you tend to find, and maybe some people have heard this phrase from their QA team, can we have more time to test this release? Has anyone ever heard that? Right? Well, if you give them more time, it turns out the release after that will be even bigger because the developers kept putting more features in. So you get more and more features in a release. It's harder and harder to test. So the correct thing to do to get around that is actually to shrink the size of releases and do smaller releases more often, and to break the releases into multiple pieces. And this is really what microservices is about. What you're trying to do is not have one release plan where everyone's trying to coordinate, 100 people trying to coordinate around it. You have multiple release plans with a handful of people for each. And you can do it, then you also get the ability to use different languages, different systems, different development approaches. The front end, the middle tier, all different kinds of things can use whatever they want because they're not all lockstepped on a single release model. Now, when you've got multiple things, you want to bundle them together into a common platform. And a common way of doing that now is to put things in Docker containers, and your deployment platform just says, I know how to stick containers out. With Netflix, we used Amazon Machine Images, because going back 5 years ago, that was the right thing to do. And Netflix is now moving to use more Docker. Now, if you get a failure now of one of these components, you find some bugs, you just redeploy that one piece. You didn't block everyone else. So you don't have one bug blocking the release, blocking the work of a huge number of people from reaching customers. What it really comes down to is you want to actually end up changing one thing at a time. Because if you change that one thing, and if you can deploy things efficiently enough, because putting a Docker container out there takes seconds, right? So why would you do that every 2 weeks when it takes seconds? You can do it 10 times a day per person or 1,000 times a day per person. There's no reason not to do it as often as you need to. But what you can do then is make each release be a single thing, which means that it's really easy to tell whether it worked. It's easy to back it out if it didn't work, and you're not disrupting everyone else. So the coordination time, it turns out to be the biggest thing that's slowing everyone down. So what's happening then is as we reduce the cost and the size and the risk of change, we increase the rate of change. So this isn't, we're not doing the typical 6 monthly releases. We're not doing those 10 times a day. We're releasing tiny fragments of a release, one feature or one update or one bug fix at a time. And you've got a continuously evolving system. Right. Now, if you're coming from a world where we go and we have a project and we're going to upgrade SAP for the next 9 months, and then everyone sort of gets exhausted and runs away from it, and wants to do something different. It's a very different model. This is an ownership model where you own the thing in production, you own its evolution, you own making it better and better all the time. So this, there are labels for this, but mostly when people talk about microservices, they're talking about the architectural patterns that people use to do this. And my definition is here, and I'll just sort of pop up some more bits here. You want it to be loosely coupled so you can update different pieces of it independently. And you want to have a bounded context because that's how you decide what is the right size for a microservice. How big should it be? How many different things should you put in it? And what you really want is to have each microservice do one thing. Right? It should, when this applies to the data tier, you end up building data stores that do one thing. So you have lots and lots of Cassandra clusters. You don't have one Cassandra cluster with lots of key spaces in it or a huge schema with everything mangled in together. You've got lots of denormalized stores, and they all work independently. They scale independently. They're owned independently. And you typically put a data access layer in front of them that you funnel everything through. So you're trying to turn everything so it looks more like a REST interface. They actually don't care what's behind it. This is one of the common patterns is, say you're on MySQL, you want to get to Cassandra. One of the open source Netflix projects called Stash, Storage Tier as a Service over HTTP with 2 A's, Stash with 2 A's in it. And that is a Java app with an HTTP interface, and it has a Cassandra client library in it, and it has a MySQL client library in it. So you put that in front of MySQL, start using it, then you add Cassandra, and you start gradually breaking pieces of your schema off, and then gradually you end up all on Cassandra. But you've abstracted it up into this data access layer, so you actually don't care what's behind it anymore. Right? So that's the kind of pattern. There's a whole lot of books that I think are interesting in this space. In particular, the domain-driven design book, it really talks about these bounded contexts and how you decide what goes in and out of a service. If you're trying to build really, really reliable systems, and one of the reasons people are interested in Cassandra is because it has these sort of very robust modes, you need to understand the Drift into Failure book, because that explains why these perfectly reliable systems will occasionally fall over, because they hide all the brokenness until all the things that are broken gang up on you, and finally it tips over, and you find 10 things are broken because it was so resilient, it was hiding the 9 other things that you didn't know about. So you have to understand how to get in there and root out the things that are going to bite you later. As you build systems that are more and more highly available, this book is a very key book to understand. So I'll talk a bit about these microservices and cloud native and monitoring. So what we've got here is, in the cloud native world, is a very high rate of change. We have code pushes causing floods of new instances, floods of new metrics, and there's a very short baseline for analysis. The configurations are very ephemeral. They don't live for very long. They could even live for less than a second. Some analysis of Docker lifetimes show that the most common lifetime for a Docker container for over about 3 or 4 month period of New Relic monitoring all the Docker containers they monitored, the most common lifetime was 1 minute, right? And the second most common lifetime was 0 minutes. Right, less than a minute. And then, more than 1 minute was way down. There was a graph with 2 tall spikes and a whole lot of small spikes, right, minute by minute. And these microservices are calling each other in complex patterns. And if you just look within Cassandra, Cassandra is sort of a microservice architecture. The flow between Cassandra nodes is actually fairly complex, with all the gossip and the hinted handoff and all the replication. So when you look at how do you scale microservice patterns and how do you monitor them, one problem is managing the scale. And it's not just the number of machines. There's this big complex hierarchy. You have it distributed across continents and regions and lots of zones if you're on AWS, or data centers if you're on your own systems. There's lots of different versions of things running at once. There's lots of containers, and you can have tens of thousands of machines. So how do you deal with that? And one problem then is, what's the flow look like? You know, when you have a monolithic app, you hit one side of it and you stayed inside it and then it popped out at the database, right? That's relatively simple. There's no real flow there. But when you build these microservice systems, you want to know what's going on. So there's a few flow visualization tools out there. The left one is a Netflix one I don't think they've released, but called SALP. Top right is an app dynamics flow, which works up to a certain amount of scale, but once you get into huge numbers of microservices, it can get more challenging to visualize. On the bottom right is the output from a Twitter tool called Zipkin, which is a flow-based monitoring open source tool, which is currently in the process of being turned into a more standardized thing. So there's an open Zipkin project that's going on right now. So that looks like a place where we could standardize things. But if you look at the architecture diagrams of a lot of sites, this is kind of what they look like. You have hundreds of services talking to each other, and you have what I call Death Star diagrams. Everything turns into a big circle, and you can no longer see what the structure is. And that's a problem because we have interesting failure modes that are part of the structure of the system. And when we look at failures, we want to understand that a zone went down, not that looks like about a third of our machine suddenly disappeared, right? If you get a power cut or you lose connection, you need to understand structurally that this is everything in this zone broke rather than everything else. So, I mean, you should know this, right? If this is a sort of a diagram of a three-zone system, you've got a load balancer at the top, then you hit an API proxy, you hit a bunch of business logic, then there's one of these data access layers, and in the back I've got a 12-node Cassandra cluster with 3 nodes in each zone, right? The traffic comes in, and when it writes to Cassandra, and that's how the data gets to the other zone. So the next request can go to a different zone, and the data's already there. So this is typical three-way replication. Should be pretty familiar to anyone that's playing with Cassandra. Now, if you lose a zone, what does your monitoring tool say if you lose an entire zone, right? You're probably going to get a massive flood of errors. The system's going to, your logging, your monitoring system's going to sort of complain mightily, right? But what should it really do? It should give you one message saying, you're still up, but don't mess with it. You lost all your redundancy, right? Because Cassandra's designed to run on 2 out of 3 zones. That's part of the point, right? That's why we were doing this. So the fact that you lost an entire zone's worth of systems isn't actually an outage to the end user, or shouldn't be, right? Maybe there's a few retries as it sort of glitches a bit, and you want to get into the ELB and have it stop sending traffic to the dead zone, but that's basically it. Your infrastructure's still working. But you probably want to stop doing maintenance on taking nodes out of service out of your Cassandra tier, because then you're down to 1 instead of 2, and you don't want to go below quorum. So it's a very different kind of analysis, and I'm still looking for tools that can do this level of understanding of what's in the infrastructure. So this is the challenge, and this is the thing I've been working on that I want to talk to you a bit more in my remaining time, is about I'm trying to get people interested in collecting these architectures and modeling these kind of failure modes, and that's why I'm building this simulator where Cassandra is a key part of what I'm simulating. And the problem here is if you want to test a monitoring tool at scale, you can just deploy it, right? But if you're deploying 5,000 nodes on AWS for testing, and you need to have them there all the time, that gets expensive pretty quickly if it's just for testing. If you want to prove you're on 10,000 nodes or 20,000 nodes or 30, what typically would happen is someone would turn up at one of the big companies like Netflix, you point your nice monitoring tool at it, and it would sort of explode on impact. It would just go, I can't deal with this, it's too big, and no, sorry. No, I can't do 1 trillion things in an hour a day or whatever it's doing. So it just gets too expensive. So I came up with an idea of using simulation to do this. And this diagram is actually part of the output from the simulator I built. And what I've been doing is modeling and visualizing microservices, and this is running inside my laptop in 1 gigabyte of memory rather than running on Amazon in 10,000 or 100,000 instances, right? Which is a lot cheaper because I already have my laptop and I can actually develop code on it easily. So the code's on GitHub. there's a front end that's using D3. It's a JavaScript front end. And there's a back end written in Go. And they aren't really connected together yet. One of the things I'm gradually working on is getting it so that the front end and the back end, you can actually control the back end in real time and visualize what's happening. What happens now is you run the back end on the command line. It saves lots of files, which you then visualize to see what's there. So how do I define that architecture? Well, here's an architecture. I wrote this up for this talk, right? So this is my architecture definition file. It's a JSON object. It basically says, I've got an architecture. It's got a description, which is for this talk. One of the things I have is a chaos monkey. So one of the nodes gets deleted at some point during the simulation, but I didn't need that, so I didn't give it a name. And then I've got these tiers. And the first one you can see, I just call Cassandra. I have a package which implements the behaviors, and I'll show you what that looks like later. But this is a Go package which pretends to be the sort of Priam Cassandra mix. Priam is Netflix's management tier wrapper for Cassandra. So I put the two names there. And it depends on itself, which means the Cassandra nodes talk to each other. So my dependency list for Cassandra has to list Cassandra, and you can have any name. You can create as many Cassandra clusters as you want doing this, right? I've got 6 nodes in one region. The next one is my stash data access layer, which is just a REST data access layer, so I just called it REST data. That depends on Cassandra. I've got 6 nodes for that too. Then I've got my business logic. Carry on is the name of the Netflix project for generic business logic. I've got 12 of them. It depends. This is a very simple app. It's just straight through. I've got an API proxy. I have a load balancer. And at the top, I have sort of the DNS entry. Denominator is the name of the DNS management layer, that thing that Netflix built. But the point here is that at the top level, when you're doing globally distributed systems, you have to have something that isn't in a region, right? So it's in 0 regions, and there's 0 count, because it's just a DNS entry. And you can see that the ELB, there isn't actually an instance for the ELB. It's just a thing, but there's one per region. So that's why those numbers are set up that way. All right. So when you've done that, what it looks like, hopefully you can see this, the architecture, the leftmost thing, is the purest form of this architecture. It's just one of each, right? So at the front, I've got, can I bring a mouse here? Oh, I should have a pointer. This is basically filtered down. At the back, I've got those three largish blobs with a triangle. Those are the Cassandra nodes in each zone. So this is basically boiled down to show you one thing per zone, right? So there are actually several Cassandra nodes per zone. And the next one over is actually the expanded version of that first one, just showing you everything, but not collapsed into a single node, right? So at the back now, you can see there are 6 Cassandra nodes all talking to each other, right? They're all cross-connected. The next thing I did was I said, let's just make it twice as many. So I can scale up. I can trivially scale this simulation up, and I said, make it 200% bigger. And then the third one, I made it 400% bigger. So now I've got a 24-node and a 48-node Cassandra cluster, 3 zones. And I can make an arbitrary complicated architecture and scale it to an arbitrary size. And at various times, I've had 100,000 nodes running on my laptop. Yeah, about a couple of gig of RAM, which is ridiculous to try and do in real life, right? So the point of the simulation is I can create architectures that you couldn't really create in real life. Either you couldn't create them at all, or you couldn't create them cost effectively. So what I'm trying to do is model these architectures. The next thing I can do from that same file, without any changes, all I did was, this is all I specified. I can tell it to have up to 6 regions. So then I do multi-region Cassandra. And the first one on the left, that's a 2-region one. Not sure if you can see it. The contrast isn't that great. The dot in the middle at the top is the endpoint that splits by DNS to the 2 sides. And you can kind of see there's 6 zones there in 2 regions. And then it goes into this Cassandra cluster that's all clumped together in the middle, right? And the one on the right is 3 regions, right? So again, I'm just now simulating a 3-region node. And by the way, every one of these nodes has a name which looks like, you know, US East 1, blah, 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 and it has an IP address assigned to it, which is actually a real AWS IP address stolen from their address ranges. So the system can export to monitoring tools as if it was a real machine with a real name, with a real Amazon IP address, even though it's just faking it all in my laptop. And this is what 4, 5, and 6, and by that time I get back to my same problem that I had previously, right? This still that's looking like a Death Star. So you can see 4, and then I just gave up trying to stretch everything out, and it's all sort of into a big blob. Now, this is a simple system. It's got one cluster. It's just got a few things connected in front of it. I tried to create something more realistic. This one has 3 different Cassandra clusters, 2 of them sort of overlapping each other there, and 2 different endpoints, which is, again, a fairly simple thing. But you can see it's getting harder and harder to visualize these systems. So there's 2 things I'm trying to do here. One is to create these architectures, which you can then feed to monitoring tools and say, can you figure out how to visualize this better, please? So I'm trying to offend people by showing them badly visualized things to get them to build better visualizations. So there are some people out there using my tool to generate architectures which they're then feeding into their monitoring systems in order to figure out how to display things better. There's a company called Instana that's actually using my tool. And I've been talking to other tools vendors about this too. So that's, you know, I could get this to be so complicated I can't see it. So when we can render this better, maybe I'll generate some more complicated ones. So anyone here ever written any code in Go? A few Go programmers? Okay, so the code I have isn't very idiomatically Go code, but somebody told me it looked more like Erlang. But this is what the thing looks like, and it ends up being the entire package that implements all my Cassandra behaviors is about 200 lines of code. I wrote about half of it in a few hours on a plane last weekend while flying back from the UK. So, you know, in 4 or 5 hours, I was able to do a fairly significant upgrade to it. So basically, every Go routine is simulating, which is a thread basically, is simulating a real machine, right? So where you'd have an instance or a container or something you want to model, I have a Go routine. And it just sits there in memory, and I have channels for connecting them together, and I can send messages back and forth at a few 100,000 messages a second, right? So that's basically what's going on. Every service looks roughly like this. It has a listener to a channel, which is basically like it's kind of faking HTTP using Go channels is the way to think about it. And then it basically says, what kind of message is this? And it's got a whole bunch of messages that it deals with. And that's what it looks like. So it's very simple. Now, when messages come into this flow, because those old diagrams I was showing you weren't just pretty diagrams, they're actually they are recording the architecture of my Go program. And every line on it is a channel that has traffic that's going on it, right? So all of those diagrams were all fully connected. Now, when you send messages through the system, it records the flow it took through the system. And I'll show you what that looks like. So here's my stash making one request. This is a single request coming into the Cassandra system that I'm simulating. And the second thing, it says T, P, and S. So S is the span. A span is a connection between 2 microservices, right? So that's the span, right? Each span has a unique number. The T is the transaction or the request, and every request that's related has the same transaction. So when you hit the edge of this system, it creates a new transaction number, and then the one in the middle is the parent span. So at every time you land in a microservice and you want to call out, you take the span that got you there and you stick it in as the parent, and that way you can actually build this tree. So what I've got here is a put going into Cassandra, a multi-region Cassandra cluster that wanted to replicate the data, and this is actually what happens in the simulation. Each of these little arrows is a message flowing over a Go channel in my program. But anyway, so it comes in, and you see the first line there is the put, and then it goes in, all the rest of them are replicate calls. So the first thing it does is 908 and then 909, which is sending it to zone A and zone B because it was already in zone C. And then it sends 910, which is the remote replica to US West 2, goes to zone A there, which copies it to B and C. Now, the very crummy simulator I've got right now does actually have token-based sharding in it, but the only people that know about the shards are the nodes themselves, and they don't know about the remote entries. So when you're talking to somebody, you don't actually know what their shards are. It's not, Cassandra has this full view. Every node knows everyone's token in the ring, right? Well, the way I have it, I don't really know that yet. So I've got to tinker with it a bit more. So the reason there's another series of calls is because I landed in zone B, Cass 4, and it turns out that isn't the right owner for this piece of data, so I have to copy it to one of the other nodes in zone B. So this is how I made sure my algorithm worked. This is the code I wrote on the plane last Saturday, basically getting this to work. So the interesting thing here, if you want to play around with gossip protocols, this is a great platform for playing around with stuff like that. It's basically a protocol simulator where you can create arbitrary protocols with arbitrary forwarding logic, and you can go and explore what's going on. And we're gradually getting better simulations, better visualizations of the flows. So I want to take these flows and put them into a much better trace visualizer, and I want to get the output to be in Zipkin format so that it basically can feed anything that knows how to do that. All right, so why am I building this? Partly because I think that tools are currently doing a bad job of monitoring these large-scale configurations, and particularly systems with Cassandra in them, where you've got a lot of internal structure to Cassandra that very few tools really understand. So I'm trying to get people to understand those structures. I also want to be able to grow and shrink this, have auto-scaling, so that this network that I've created is not a fixed network. It grows and shrinks. It's actually a dynamic graph. And I can grow it, I can shrink it, I can actually forget nodes, I can basically have chaos monkeys killing things, and I can forget links, I can create partitions. So I can have a globally distributed system with traffic running through it, then I can cause certain types of partitions, and I can cause types of outages, and then I can try and make sure all the simulators can handle that. So that's where we're going on. So just the takeaway on that, if you want to know what's really happening now in enterprises, the Lean Enterprise book really documents the struggle that a lot of people are going through to get things brought into this modern age. It's sort of the enterprises trying to learn how to do continuous delivery. Building Microservices is an awesome book for figuring out all the different transitions you have when you're trying to get to this place. And I think Cassandra has a really key place in the whole microservices continuous delivery transition. So we started a little bit late, but could take a few questions. And like I said, I work at Battery Ventures. These are the companies that I mostly play around with. This is our current portfolio. So if you want to talk to me about any of these companies, happy to do that. Any questions? Yep.
So one table to a microservice, that fits fine. But the same table should be addressed by other microservices too. That would be all right.
So talking about the mapping of tables to basically clusters and microservices. The way, you can do it lots of ways, but the sort of best practice way I think of building out a microservice architecture is you want to own the data sources. You want to own a data access layer and force everybody to go through that data access layer. You don't want anyone else accessing your database. You want to be able to hide any maintenance work or upgrades or anything you might want to be doing. You can hide it behind that data access layer, which means your business logic code is all using REST calls into the data access layer from everywhere else. At Netflix, that's enforced using security groups. So the only thing that Cassandra trusts is its data access layer. Right, and everyone else has to go into that. So that's one model. You're optimizing differently here. So you've got a very denormalized data model. Your writes are sprinkling across the system, and you have to have checkers that make sure all these databases stay in sync. So there is some work to be done there, but that can also happen in the data access layer. You can have threads running there, and maybe at night when it gets quiet and traffic drops, you've got some extra capacity, and you can use that capacity to make sure that all of your foreign keys exist, and all the references, all the cross-referencing between clusters actually still works. Right? Yeah? Am I out of time now? All right. Thanks, everyone.